Hi students, Professor Nugent here. In this video, we're going to discuss predicting y when the dependent variable is the log of y. Right, so you have a model which is log transformed in a dependent variable, but you want to get that prediction into units that you can easily understand. Now, say we have this model, log of y hat, estimated, predicted, is equal to beta naught hat plus beta 1 hat times x1 through beta k hat times xk. Using this expression here, y hat equals to the exponent of log y hat, systematically will underestimate the predicted value of y. So we have a couple of different ways that we can get at the predicted value of y when we have log transformed our value y back into units that we can understand. So if we have taken a log transformation of, say, income or the log transformation of price, we want to get that back into dollars, right? So that we have units that we can understand. One of the ways that we can do this is, assuming that the errors are normally distributed, we can take the exponent, e to the power of the estimate of error variance over 2 times the exponent, e to the power of log hat of y. All right, so, but the thing is that this assumes that this requires that the errors are normally distributed. And we can come up with other ways to do this without needing to assume that the errors are normally distributed. So let's do that. And we have 2 ways to do that. It's like Burger King, you can have it your way. So without assuming that the UI are normally distributed, but we do need to make assumptions 1 through 4, we can derive a method that is similar. So we want to get the expected value of y given x. That's going to be equal to some value alpha times x of beta naught plus beta 1 x1 through beta k xk. All right, and what this expression represents when estimated is y hat is equal to alpha naught hat times exponent, or e to the power of log of y hat. All right, log y hat is equal to that equation. Take the exponent of log y hat, you get that thing, and then we need to multiply it by this scaling factor. And alpha hat is the estimate of alpha. And what alpha represents is the expected value of u. So we need an estimate of alpha. One way to estimate alpha is to do the smearing estimate. And in that case, alpha naught hat will equal the 1 over n times the sum from I equals 1 to n of x u I hat. So you can take the exponent, or e to the power of the residual, where the residual from the estimated regression, right? And just sum that times 1 over n. So that is one way. Another way is to do a regression estimate. So a regression estimate, we start with E, expected value of y given x is equal to alpha naught x beta naught plus beta 1 x1 through beta k xk. And we're going to simplify this notation and call that mi for observation I. Okay. Now we can estimate mi hat from the e to the power of log of yi hat. Then what we can do to get an estimate of alpha is use a simple regression without an intercept. And this is going to be like a y check. The regression of y on alpha. We're doing a check to differentiate it from the smearing estimate. This is the regression estimate on mi hat. So we're regressing y on mi, right? With your no intercept. Regression of y on mi, and the estimated coefficient is alpha naught check, right? So alpha naught check or alpha naught caret, however you want to call that symbol, is a sum from I equals 1 to n of mi hat squared negative 1, sum from I equals 1 to n mi hat yi. All right, so two different ways. This second way, you may end up getting an alpha naught check less than 1, and in that case, that may show that this method is not working, because alpha naught should be greater than 1. So let's talk about a way to consider how well this worked. Let's think about the goodness of fit. How well did this work? We can check goodness of fit two ways. One, we can look at the square of the correlation between yi and mi hat, and we can compare that to the r squared from a regression on yi. So a regression of yi equals beta naught plus beta 1 x1 through beta k xk. So what are we asking here? How well does the log model explain y versus this linear model explaining y, right? And if we have a higher r squared with log y, that is evidence that we may want to use log of y. All right. So second, you can use sum of squared residuals where ri hat is the residual is equal to yi. minus alpha 0. Check exponent, or e to the power of log of y hat. So yi minus that estimated value. And then we can use 1 minus sum from I equals 1 to n, ri hat squared all over sum from I equals 1 to n, yi minus y bar. And again, we'll compare this to the r squared of a regression where on the right-hand side you have ri. So we're thinking, how well does the log model explain y versus just a linear model? And if the log model is explaining y better, then we want to stick with the log model. All right, so that's it for predicting y when the dependent variable is log of y.